All right, so far we've talked about nodal analysis. We saw that nodal analysis is a method for dealing with circuits, and it's based on applying KCL to the nodes of interest and expressing that in terms of voltages. Now, in circuits and systems, as well as probably in a lot of places in real life, there is this duality, and you will keep seeing it. There's a dual of everything, and a lot of times what happens is interesting. It's not a very it's a little bit more sophisticated the way the duality happens. So the mesh analysis is really the dual of nodal analysis. So think about it this way. Now, if you were to reconstruct it based on what we just said, what I just said, that the nodal analysis, the mesh analysis is the dual of the nodal analysis, what do you expect it to do? So first of all, the variables in the nodal analysis were the voltages of the nodes. So what do you expect the variables to be in the mesh analysis? Currents of meshes. It's mesh analysis, right? No. Nodal analysis is the voltages of the nodes. Currents of the meshes, right? And we talked about meshes before. Those are the smallest loops you can define. The window panes, if you will. So it's the currents of the meshes. Now, what did we apply? What was the sets of equation? What was the rule that we applied explicitly to the nodes in the nodal analysis? We applied KCL. Now, so what do you expect we're applying? We're applying KVL to the meshes, right? As opposed to KCL to the nodes. And what do you expect that we write them in terms of? The currents of the meshes. The same way that we wrote KCL in terms of the voltages of the nodes. So when I say it's the interesting duality, it's an interesting duality really in that sense. So let's do it. Let me show you what it means. And we are going to spend a lot less time on mesh analysis than nodal analysis for the reasons that will become apparent soon. So I'm just going to show it in the abstract form. So I'm not going to show the actual branches here, for example. Let's say, so each one of them is a branch. Let's say each one of them is an element. I could have, oh, I can do it, I guess. Suppose I can avoid being lazy and do it. But if I draw something like that, I want you to understand that I mean that abstraction. Okay, let's just even do it this way. Okay. So one thing that's interesting is that there's no ground by definition. There's no fundamental need for a ground. Now, what do I mean by mesh currents? So let's assume that, so what are the meshes? How many meshes do you see here? 3. How many loops do you see here, by the way? 6, right? The 3 meshes plus this loop and this loop and this loop. So, and you also know that relationship, right? The number of branches is the number of meshes plus the number of nodes minus 1 that we derived the first time. So but the mesh currents, what do I mean? So let's call this mesh 1, I1. This is I2, and this is I3. Now, this is a little bit, this may be a little bit counterintuitive or not as intuitive as the other one in the beginning. What I mean by these mesh currents is the following. Now, if I ask you the question here, what is the current through this element? What would you say in this direction? It's just I1, right? Or for that element, going in this direction is I1. What is the current through this element? Let's say going in this direction. So what is this current in terms of the mesh currents? I1 minus I2. So this is I1 minus I2. So it's a superposition of these things. You superimpose these currents and you look at the algebraic sum of those. And if, likewise, if I ask you what is this current, let's just do it here, less crowded. I2 minus I3. And if I ask you what is this current, what would you say? I3. And if I ask you what this current is? I2. And what is this current? Negative I2, exactly. Okay, so good. We are all on the same page in terms of concept. Okay, so the mesh analysis is essentially that. Essentially, you write the KVL for these different nodes in terms of those mesh voltages, and that's it. So I think probably it's best if you do an example first. Let's do an example, and we'll discuss some of the subtleties and challenges and interesting things that happen. So the example I have here for you is not that complex. So let's say So voltage source, resistor, resistor, resistor. Another voltage source, let's call this a V1, 16 volts, R1 of 4 ohms, R2 of 2 ohms, and R3 of 3 ohms. V2 goes 1 volt, and that's it. So how many meshes do we have? 2. So we need to define 2 mesh currents. So the meshes that mesh currents that we define, you can call this I1, and we call this I2. So we are writing KVL. So we have to go around a loop, which is basically in this case a special loop, which is called the mesh. So what is the KVL around the first loop? So we are going through, let's start from here. We are going from negative to positive in the V1, so you get negative V1, this voltage. Then what do you see? What is the voltage drop across this guy going from here to there? This resistor. R1, I1, right? That's the current through that resistor. What is the voltage drop across this one from here to there? You remember what's the current through this guy? Remember these guys that are shared between 2 meshes? So it's going to be R2 times I1 minus I2 equals 0, because we're back to the same place. That's KVL around mesh 1. And then going around mesh 2, what do I get? I can start from somewhere. I don't know. I can start from here. Right? So I'm going into the positive terminal, so I get a V2 plus. So I'm coming up here. What is the voltage drop across here from this end to that end? R2, I2 minus I1, right? Because that's the current going in this direction, exactly. Plus, what is the voltage drop across R3 from this side to that side? You have to keep track of direction, right? R3, I2 equals 0. So I have these 2 equations. I can reorder them. And when I reorder them, you can easily see I can write them as in matrix form. I can write it as R1 plus R2. So I'm multiplying them by I1 and I2, and I'm getting a vector of voltages on this side. So I get R1 plus R2 I1, negative R2, and then it's going to be, once I move it to the other side, it's going to be plus V1. And here I will have, for I1, I have negative R2, and then I get R2 plus R3. And then this guy goes to the other side, you get negative V2. Do you see the similarity, conceptual similarity, not exact, to the nodal analysis? If I ask you, how would you come up with this matrix by inspection, by looking at it in the mesh analysis, what would you tell me? It's the sum of the resistors attached. Diagonals are some of the resistors attached to a given, not attached, some of the resistors that are on a mesh. Right? These 2 resistors are the R1 and R2 are on mesh 1, and R2 and R3 are on mesh 2. And the diagonal, the off-diagonal terms are negative of shared resistors between meshes. Exactly. Right? See? Yes?
Do the circles always have to be counterclockwise, or do you have to find it clockwise?
Well, in this case, they're clockwise, actually.
Oh, sorry.
But it doesn't matter. It doesn't matter as long as you keep it consistent with the equation, with the polarity. So if you define them in opposite direction, what you will get, you get a negative of what you would have gotten otherwise. Okay. But I don't see why one would want to flip them back and forth. If you want to make your life more difficult, by all means. Yes. But you have to keep track of it. There was another question, or? Okay, no. All right, so you can see this, right? You can see that's happening here. And these have names too, right? And this is the stimuli vector. Now, so this is the matrix Z, and this is the vector I which is equal to the Vs, the voltage stimuli vector. And we can put numbers on it and solve it. I mean, if you want to just like, we can do that. I mean, we can plug these numbers in and make a numerical example and solve it. You would just invert that matrix and multiply it by. So we've done a couple of those, so I think that's enough. Unless do you want me to do it, a numerical one? Anyone? Okay. But you should be able to. Yes?
We usually mention that going across the voltage source is negative voltage and going across the resistor is positive.
Well, I'm looking at what happens to my voltage, right? So I'm basically going here, when I'm going from here to there, I'm going to the negative terminal. So essentially think about it as this voltage is going up and this voltage is going down. So they have to have opposite polarity, right? So now I could have made this my convention that this is positive and then this would have been negative. If I define the voltage drop, so it's a convention. But you need to be consistent. You can't just do one differently from the other. Both of them, either you say, okay, this is the amount of voltage that I will go, the actual potential. So the actual potential goes up, so this becomes positive. These all become negative because they're dropping, or vice versa. So it's a convention. You pick one. This way, what happens is that then you can, on the other side, you will see which ones are, you can, again, do it by inspection. These are the voltages that are increasing in the direction of the mesh. So if the voltage is increasing in the direction of the mesh, it becomes positive. If it's decreasing in the direction of the mesh, it becomes negative. But yeah, that's a good question. I mean, it's like, why did we pick the currents leaving the node as opposed to entering the node? You can do it. Some people actually do it the other way. There are some books that do it the other way. It's equally valid. Yeah, good. Any other questions? No? All right. So this is the Z matrix times I, and of course, when you try to, what you're trying to solve for this time is I, right? You're trying to find the mesh currents. So I is going to be Z inverse times the stimulus vector Vs. Now, here's one thing that you need to be very, very careful, and I want you to pay attention to. And I want everyone to pay attention to this thing. You may be tempted to think that Z matrix, because it's made out of resistors, is the inverse of the Y matrix. You may not be tempted by that. That's fine. But if you are tempted by that, beware. There is not a very direct and close relationship between them. Because if you think about it, there shouldn't be. They're not even of the same order. They're not even the same size necessarily, right? The number of nodes and the number of meshes do not have to be equal, or they don't have to be one off by one, because the nodal equation gives you n minus 1 nodes. So if this is the number of, this is, in any circuit, this is going to be the size of the matrix, the order of the matrix for the nodal equation, right? Nodal equation gives you an n minus 1 element by n minus 1 elements if you have n nodes, because 1 is ground. This is the number of meshes, right? Which is the number of equations, or the order of this matrix in the mesh equation. There is no known relationship. It depends on the number of branches. So they don't have to be equal at all. Right? In fact, in most cases, they aren't. Excuse me. So that's basically the situation. So that's Z matrix inverse. So Z inverse is not equal to Y, or Y inverse is not equal to Z. They don't even have to have a very close relationship. Now, okay, so this sounds like a reasonable method of analyzing things too, right? But I would say this is much weaker than nodal analysis. And I'll want you to think that why it is. Why do you think this is, why, anyone has a guess? Why this is, I say, much weaker than nodal analysis, unfortunately. Any thoughts? Okay, let me just present a couple of examples to you. A couple of things to see why that happened, why I said that, or if I can justify that statement or not. So let's start with something, a circuit. I'm going to draw a circuit here for you. Okay. So let's say you have a circuit that looks like this. This is going over actually. So. And you can put a voltage source anywhere you want, just put it here. So let's say this is R1, R2, R3, R4, R5, R6, right? So if I show you something like this and I ask you, where are my meshes? What would you say? Well, say meshes are meaningful. I said window panes, right? But it's kind of like there's no real window here, at least the way I've drawn it. But can I redraw this in a way that actually allows me to flatten it, essentially, so I can define meshes? Can I redraw it? How? No. I mean, I want it to be on a flat surface, right? I mean, I want to flatten it. Yes?
You can like click and drag that bottom node into the middle.
I love the way you said. You said click and drag the bottom node to the middle. I love it. No, it's actually good. That's correct. Yes, that's one way. Yes.
You could just move R5 and R6 outside.
You can move the R5 and R6 outside the box. Both of them are valid statements. So the first one was click and drag this to the middle. I love it. And when I click and drag that to the middle, this is the way it's going to look. Right, so then R1, R2, R3, so these are equivalent. R4, oh, I didn't give these a name. R7, R8. R7, R8, R5, and R6. Now, do I have meshes? You bet I do. How many do I have? How many meshes do you see? 5 meshes, right? 1, 2, 3, 4, 5. The other suggestion, which is equally good, is take the R5 and R6 and take it to the side. Just click and drag. R5, click and drag. You know, when I was growing up, if somebody said something like click and drag, nobody would have understood. So what are you talking about? R3, this is R4, R1, and whatever, R7 and 8. So now, yeah, I have another one. And how many meshes do I have? Again? 5. Are they the same meshes? Not exactly, right? Or are they? Do you see this mesh? Do you see this mesh in this one? Let me just point it out. This mesh, for example. Is it a mesh now? It has become a loop. So that mesh is not there. And there's a new mesh which wasn't there before. It's this mesh, which was a loop before. So my meshes have even changed. Now, this brings us to the concept of topology. We refer to circuit topologies. So you may hear topology. Constantly, if you're in the circuit design, say, yeah, use this topology or that topology, right? That's why they refer to it as topology, because these are topologies, the exact position. I mean, it's the way they're connected that matters. So topologically, these three are the same. And that's why constantly you may hear people referring to circuit topology, this circuit topology, that circuit topology, et cetera, because it's the way it's drawn. And that's important because, you know, a lot of the concept and intuition comes from the way we draw things. But nonetheless, so do I have any problems so far? Did I present any problems to you? No, right? This still is good. I have 5 meshes. I can write 5 equations and 5 unknowns. I have get a 5 by 5 matrix. Good luck. Yeah, anyway. But it's, from a mathematician's perspective, it's solved. Once essentially a problem is reduced to a linear algebra problem, most of the times it's considered solved from a mathematician's perspective, but not from an engineer's perspective necessarily. We need the answer. So, and more importantly, we need a way to think about design, but we'll come to that in a sec. But no, so far so good. How about if I give you a 3-dimensional circuit? Let's say something like, I give you one of those things that sometimes people like to give you a cube of resistors. And I say I have a voltage source here. Is this a, can you define meshes in this? The other question, more accurately, is this planarizable? Can you planarize this? See, this is what we did. We planarized these things. So nothing crosses nothing else. Because if things start crossing like this, and if we can't resolve these crossings, then we have problems because we can't really define clear meshes. It's like a window pane where the glass is bent and goes through itself, like a Klein bottle or something like that, right? Klein jar. Right. So can this be planarized? Yes. Stretch the back one over everything. Over everything. Yeah. Okay. You can do that. How about inside everything? That works too, right? Yeah. It's easier to draw for me now. Yeah. But you're right. You were right. What you said is correct. What he said is that take the back wall. Okay, so I'm going to say something slightly different. Take the back wall, shrink it, and put it in the middle of the front wall. So as if you're taking a perspective view straight from the front. Right? And then it will look like this. If you look at it straight from its face, look straight down its face. That's what the way it will look like, right? If it was a 3-dimensional object. So now it's planarized, right? So I can define meshes. How many meshes? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Fine. Still, I haven't presented a problem to you that cannot be solved with mesh equations. Okay, now I'm going to create one. Okay, well, I don't know. Just add one more resistor across here. So where is it connected? It's connected from this node to this node. Now, can you take it out somehow without crossing anything else? Is there any way to take this somehow so it doesn't cross anyone? So it's crossing here, right? You can't. Right? So now you can't apply mesh equations to this, mesh analysis. So, well, this was one example, but there are lots of circuits that you can create where this is going to be a problem. The more elements you add to it, then the more of these problems you will have. So it works only for planar circuits, unfortunately. And that's the problem. And that's why it's a lot weaker. Now, the reason we do mesh analysis is interesting, right? It is because we want to understand the concept, and there are certain cases that's useful. Now, one question about mesh analysis, one more question about mesh analysis. So let's go back to the mesh analysis discussion. But we need to understand how to do it in general. So if you wanted to do this, can you think of the dual of the situation where we had, you remember with nodal analysis, we had the situation with the voltage sources? So what do you think will give us the trouble now? The current sources, right? So let me just give you an example, something like this, and see how to deal with that. And I will ask you to use powers of extrapolation to tell me how to deal with this. R1, R2, R3, R4, V1, and I1, capital I1. Okay. So, how many meshes? 3 meshes, clearly. So, what are the equations for these meshes? Right, if I were to write mesh equations, can I do that? Well, let's write show the meshes and assign currents to them, as we usually do. So this is I1, this is I2, and this is I3. Right? But you already can say something about the relationship between I2 and I3. Right off the bat, you can do that. What can you say? What is the current through this branch? What is the current going down in this branch? I2 minus I3. But what else is it? Capital I1, right? So I2 minus I3 is capital I1. An equation, a relationship, right? So now I have to write the rest of the equations. So, but if I try to do it for just meshes, for the mesh 1, it's fine. For mesh 1, what is the equation? For mesh 1, I would say it's going to be negative V1 plus R1 I1 plus R2 I1 minus I2 equals 0. So that's for mesh 1. Right? Fair enough? How about mesh 2? What can I say? Can I write that such an equation for mesh 2? I can write the voltage across here. It's going to be I2 minus I1 times R2. And the voltage across this guy is I2 times R3. Right? What is the voltage across here? What's the voltage across a current source, an ideal current source? There's no Ohm's law for it, right? The same way that there was no Ohm's law for the voltage source. So we're stuck. We don't know what this voltage is just by looking at it this way. It doesn't give me another equation. Same thing is true about this other mesh. So what do I need to define now? What do I need to kind of now use your powers of extrapolation? We had something that needed to you needed to get rid of something. In the case of the nodal analysis, it was where you had a current source and you absorbed it into a super node. So it didn't matter. So what you need to define? Supermesh. Yes. To the rescue. All right. So this is a supermesh. I mean, it technically is a loop, right? They call it supermesh. Right? It's a loop. KVL still applies to it. Not KCL. KVL applies to it still. Let's see if I can write KVL around that. Does anyone want to take a stab at it? Does anyone want to try? It's not that difficult. Yeah, go ahead.
R2I, what are we calling the current?
We don't need to call it anything. We already know what it is. The two currents are still there.
Oh, okay.
Right.
So still use I2.
I2. You still use I2. Now, here's the reason. Here's the reason. You can't define a new, I don't know, I4. Here. Why can't you do that? Because that current is not equal here and there. Right? You need to really write it still in terms of I1, I2, and I3. So you don't do that. Just write it in terms of those. Go ahead. R2 times I2 minus I1, correct?
Plus R3 I2.
I2.
Plus R4 I3.
Yes. So that's fine. It's basically you're writing KVL around this loop. That's all you're doing. The same way that you wrote KCL on that cut set or that supernode. So then you have 3 equations and 3 unknowns. You can write it in matrix form. You can do whatever you want with it. This is not a plus. Oh, R4, sorry. It's a 4. OK? Make sense? So that's the mesh analysis. The reason we do it is for some theoretical aspect and for some analysis aspect. A lot of times you need to understand these things to be able to derive the other things. For example, sometimes when the next step next week we'll go into theorems. We'll talk about circuit theorems. And you will see that some of them are derived using the nodal analysis and in some cases mesh analysis. Basically allow you to derive general properties of circuits and the theorems, which are actually more useful than these analysis tools. These are really analysis tools. What we do when we go to the theorems, you will see that they are more useful for design. And design is the ultimate objective of engineering. If you're an engineer and you want to come up with methods of analysis that help you with design, facilitate the design process. All right, any questions? Yes?
What is an element in the same wire as the current source?
I'm sorry, say again?
In the same line that has the current source, what if there's an element, like a resistor or something?
Oh, okay.
Like actually supermesh it without taking it out.
No, you can, right? So we'll get to that, okay? There are 2 or 3 different ways to deal with that. That's a good question. So he says, what if there's an element in series with the current source? Let's say an R5. What do we do with that? There are different ways to deal with that. One is that to treat it like an element. Like you can say, look, the current through this guy is I2 and I2 minus I3 times R5. But we also know one more thing that's even more obvious, right? We know exactly what this voltage drop is. What is it? It's a known quantity. I1 times R5. Now, more importantly, this is actually a good thing you brought up. So if there is an ideal current source and I have an element in series with it, let's say this is a 1 amp current source and this is like 1 ohm or whatever value, and I put it inside a black box. And we are going to talk a little bit more about this next week, but what is this equivalent to? The source itself, right? I would argue that this is exactly the source. If it's inside a black box, there's no way you can tell if there's a 1 ohm resistor there or not. Because what it does, it forces this current to be 1 amp. An element in series with a current source, ideal current source, is irrelevant. And what is the dual of that? The dual probably is more familiar to you. You said everything has a dual, right? An element in parallel with an ideal voltage source is irrelevant. This is exactly equivalent to the ideal voltage source itself. Because this voltage is fixed. This guy forces this voltage to be whatever it wants it to be. It doesn't care what this is. Yeah, there would be some current flowing here. And yes, there would be some voltage drop inside here. But it doesn't matter if you don't care about that particular value. And if you do, you know what it is. If you care about this voltage, it is this voltage. If you care about this current, it's this voltage divided by this resistor. If you care about this current, obviously it's 1 amp. If you care about its voltage, it's 1 volt because it's 1 ohm times 1 amp. Good question. But you can always analyze it. I mean, you can always throw it in and make it part of your analysis. And it will come out to be that. Yes?
What if there's like a voltage drop across the current source and across the resistor? Are they the same?
The voltage drop across the resistor and the current source are not the same, no.
Okay, so do you have to consider the voltage drop of a circle when you want to consider like the voltage drop in a whole box?
Yeah, I mean, yes, of course. When you go around it, when you do the mesh analysis, you have to write this voltage drop if you were to do that.
Okay.
Right? But then you have to define this supermesh in a different way.
But we assume the current source has no voltage drop.
Right. No. We don't assume the current source has. I'm sorry. We don't assume the current source can have an arbitrary voltage drop.
Right.
The same way that the voltage source can have an arbitrary current. We don't assume it's 0. You can't assume that. You see, Ohm's law says in a 2-terminal element, either you define current or voltage. You can't define both. The other one is determined by what else is connected to it. Actually, I had an interesting scenario with this many years ago. So there was this case where there were 2 people like fighting over a patent and all those things. So it was about a UPS. It was like an uninterrupted power supply. So one of them came and they were debating it. So I was talking to one of the guys who was supposedly, and he clearly was trying to obfuscate what he was doing. So he started an argument, and I kind of like tried to dissect it. So it boiled down to power supply which could set both its voltage and current simultaneously. So it says, I have this power supply. So he admitted that this is equivalent to a power supply that gives you 3 volts and 2 amps. He said, how's this possible? Because you still have Ohm's law. I mean, you can define one. Or you can define a relationship between one relationship, one equation between them, which is what usually happens. And the other one is determined by what you connect to it. If I say I have something that has a voltage of 3 volts, and a current of 1 amp, then it means that the load is 3 ohms. But if I apply a different load to it, it violates Ohm's law as far as that's concerned, right? If I put a resistor there. So if you have an ideal current source, you don't know anything about it. I mean, its voltage can be anything, not that you don't know anything. Its voltage will be determined by what is connected to it. If you have an ideal voltage source, its current is determined by what you connect to it. You can't define both. And a resistor is a relationship between that voltage and the current. So are a lot of other elements. A nonlinear resistor, a diode also is a relationship between those. Okay, any other questions? No. So we talked briefly, so there's one more subject I want to actually go over with you today. And we started talking about this, but I thought it's probably beneficial to do a little bit more on this subject, which is the subject of, you remember, and this goes back to the design, the diode circuits. So I'm going to we did a little bit of that, but I want to kind of like go over that process one more time. So we saw that we defined this ideal diode, right? We said that a realistic diode has this exponential behavior and it's an interesting thing. It has an interesting physics, but we idealized it. So this was the ideal diode. And we idealized it to an element that could carry a large amount of forward current with no resistance and could withstand a lot of reverse voltage without any current. So if it's a reverse voltage, it's an open circuit. And if it's a forward, it's a short circuit. If there's forward current, it's a short circuit. If there's reverse voltage, it's an open circuit. And there's a reason I'm saying it that way. Because you can't apply like a 3-volt supply to this thing without things exploding in a forward, but you can apply it in the reverse. No problem. The voltage can be negative. So this is the voltage, and this is the current. Okay, so this was the ideal diode. Now, and we started building circuits with it, and we'll continue to do that. So we saw also that now if I add a resistor in series with this, resistor R, this curve will be adjusted. So what happens is that in the reverse, it doesn't matter because it's an open circuit here. So it's an open circuit in series with a resistor, which is still an open circuit. An infinite resistance in series with a finite resistance, right? But then in the forward, what we saw is that this becomes a short circuit, but there's voltage drop across the resistor. So now you have something whose characteristic looks like this. So this is the IV characteristic, I versus V. And what the slope is 1 over R. Or G. And we also saw that if you add one, you could also kind of like shift this forward and backward by adding a voltage. So if you have a voltage V1, and let's call this R1, when you add this voltage, you actually shift it. You can shift it forward by adding a positive voltage in this direction, and this was V1, and the slope remained R1. Or you could make this negative and it would go backwards here. Now, why is that? Again, to refresh your memory. Because if I have a voltage, let's say I have a 1 volt voltage here, right? And let's say I'm applying an external voltage, this voltage, this V, is applied to see what happens. So I start changing this voltage. When this voltage is negative a large value, minus a large value, what happens is that this is reverse biased, right? So this open, nothing, no current flows. As I keep increasing the voltage, when does this diode turn on? Turning on meaning going to this point and then becoming a short circuit. At the point where this voltage becomes 0, right? For this voltage to become 0, the voltage across this guy, what should this voltage be? For this voltage to be 0. Forget about the resistor for a second, and we'll get to that in a second. Just if the resistor were not here, V1, right? Once it becomes V1, it says V1 and V1, and beyond that, it's just going to be turning on. Now, would the resistor matter when there's no current as far as the voltages are concerned? And up until that point, there's no current. So the voltage across that resistor is 0 anyway. So it's not going to do anything. So it's the same thing. It's going to be shifted this way. And of course, if I flip it upside down, just the voltage, then this will shift here. So now the other thing that we started doing, and I'm going to give you kind of like a little bit of a more elaborate example this time, is to try to construct circuits that would give you a certain transfer characteristic. And this is a useful thing. You can actually create a nonlinear characteristic of your choice, a desirable nonlinear characteristic, by creating a piecewise linear response. And these are things that you can actually make with non-ideal diodes. There will be some corrections to it, but you can actually make these kind of things. So let me ask you a question. So let's just create something and try to construct it. Okay, let's use a new whiteboard. So let's say I want to create an IV characteristic that looks like this. Let's start from here. So let's say there are 3 slopes here. This slope is 1/2. This slope is 1. Making it a little closer to 1. And then this is, let's say, 2. And then this level, this voltage is 2 volts. This next switch happens at 3 volts. And next switch happens at 4 volts. And on the reverse, I want to have something that switches at -1 volt, goes to a slope of 1, and then switches to a slope of 2. So let's say this is the desired voltage characteristic that I want to get. Yes?
Is that -2?
Yes, it's a -2. Thank you. Is it clear what we are trying to achieve? It may not be clear how we are going to achieve it, but so we need to break it down into those components, right? Those single piecewise linear elements, components. How do we do that? So we need to write it as a sum of a bunch of things. One way to think about it is a graphical way. So think about this as this is equal to the sum of a bunch of stuff. So where do I start? Let's say I start with this piece, right? Let's start with that, and I'll have you tell me what the rest of them are. So the first component is going to be something that starts at 2 volts, is 0 all the way, and its slope is 1/2. So this is the first one. So I want to make this as a sum of all these things, because if I make this as sum of these things, these being currents, I can get the sum of currents how? If I have current sources or the branches with different currents that I want to add, what do I do to them? Put them in parallel, right? If you put 2 branches in parallel, you add their currents. So I can, if I create this as a sum of bunch of curves that I know how to generate, I can create those branches and get that result. So what is the next thing I need to add to this to get to the next level? So who's next? So in the line of question answering. Yeah. Yes, go ahead.
You would have to add the same curve, but it would start at 3 volts.
3 volts, yes, exactly. So you have to start at 3 volts and add the same curve. Why the same curve? Isn't the slope there 1?
Yeah, but they would
They would add, so they basically you just get it. This plus that gives you a slope of 1, because each one of them gives you a slope of 1/2. Right? So this plus that, and then what is the next thing that I need to add?
you would have a slope starting at 4
Mm-hmm.
with a slope
This is 2.
and the previous one was,
This is 1.
oh,
1, the slope of 1, right? So it starts at 4, and it goes up with a slope of 1, because you already have a slope of 1 from these two at this point. So you can need another 1 to give you a slope of 2. So these 3 would generate this positive cycle. Is everyone clear why? Are you comfortable with these numbers? Do you understand where we got, why it became 1? Go ahead.
Is there a reason the line wasn't extended to the negative for the second one on the horizontal axis?
No. The reason is that I forgot. So the reason, no, there's no reason the line didn't extend here, no. Yes, good. All right, so that's for the positive side. How about the negative side? Well, we ran out of space here, so we'll go here, continue here, plus. How about the negative side? I want to create things that have slopes of this nature, and maybe the next person in line can answer. Yeah. So what are the things that you need to add to create this in a piecewise manner? So what would generate this slope for you first? Okay, starting at -1, right? And with what slope? This has a slope of 1. Slope of 1, right? -1 would be going this way. Okay, so it's 1. And okay, and what else? Is that enough, or do I need something else? What's the next piece? Okay, with a slope of, so starting from -2 and the slope of 1. So it's the sum of these 5 curves. But that's a mathematical or graphical way of doing this. But now if you want to make it into a circuit thing, how do we generate this? Do we know? Let's do that. Tell me what these things are made of. How do you make these? So let's make them one right next to them. So how do you make this one? Just this by itself. Go ahead. Look at that. So I would need a diode, right? And a resistor and a voltage source. What is the resistance? What is the slope here? So the slope here is 1/2. So what should the resistance be? 2, right? This is a voltage versus current, right? So this is a conductor. So it should be 2 ohms. And what is this voltage? To get a starting point of 2 volts? 2 volts, exactly. So, and how about this one? Next person in line. What would this look like? 2 ohm resistor and 3 volts. And then how about this one? 1 ohm, 4 volts. And okay, now let's get to the interesting stuff. How about this one? Do you want to? Okay, maybe next person. Yeah. How do you generate that? The same diode, the same way?
No, reverse.
Yeah, I have to flip it because now it's creating the opposite. So now the diode has to be this way, and a resistor of 1 ohm. 1 volt in which direction?
It has to be in the flipped direction.
Right, because you want, when this voltage becomes 0, basically you need to have a -1 here across this, which is cancelled by that. So this is going to be 1 volt. And then how about the last one? -2. Yeah, 2 volts. So you see these 5 components, right? 5 branches that we created, or super branch. So we can basically put all 5 of them in parallel, and it would be something like this, right? It would be mass production. Yes. Yeah. See, mass production don't work. All right. So this two-terminal element with the associated values, I'm not going to just write the volts or ohms for now. 4, 1, 1, 1, 1, 2, right? With ideal diodes produces this transfer characteristic. Right? This is a very simple example, simple design example, but it shows you the concept of design, right? The concept of design is really understanding how things work, breaking it down into simplest element, understanding your building blocks well, your ingredients well, and then putting them together in a way you want. And that's why you want to do analysis, because analysis also allows you to understand the more delicate and more generally complex relationship of these things. All right. Any questions? Yes?
How does the voltage drop of a diode work so that KVL can still work when there's no current?
How does, could you repeat that question? Sorry.
So like if for the circuit above, if V is less than V1, there will be no current.
Correct.
So how does KVL work? If there's no current, there's no voltage over the resistor, so.
Right. But how about the voltage across the diode?
Yeah, that's what I was asking.
Yeah. So the voltage across the diode can be anything, right? When you have an open circuit. That's a good question, right? So if you have no forward voltage, if your voltage is reversed, it can be anything. The current is 0, so it can absorb any voltage. The same thing in the forward path. In the forward path, it can absorb any current. All it says is that my voltage is 0. I'm a short circuit. I don't care. You can pass any current you want through me. And in the reverse, it says, you know, my current is 0. Drop whatever voltage you want across me. So that's how it works. Any other questions? If not, okay, well, see you next time.